Today we're going to look at hypothesis testing in a little bit more detail and get into the steps for actually conducting a hypothesis test yourself. So that's the name of the section, is hypothesis testing in 4 steps. There's 4 basic steps to follow. All right. So the 4 general steps, and we've mentioned these already in the previous section, but just to recap: first, hypothesize, state your null and your alternative hypothesis about the population parameter. Prepare, state the significance level, which they'll usually give you in the problem. Figure out what the test statistic would be. This can either be done by hand or be done through StatCrunch, and we'll talk about that a little bit more later. Go ahead and run the test in StatCrunch, so compute the observed value of the test statistic and compare it to what the null hypothesis said you should get, and then calculate the p-value to see if you're surprised or not to get that, and then interpret that. Does that mean you reject or fail to reject the null hypothesis? So there are a few conditions that we should check before we run a hypothesis test, and these are the same conditions we used for the central limit theorem back in Chapter 7. First, the sample has to be random and independent, so each observation is independent of the others, so is independent of the others in the sample. The sample size has to be large enough for 10 successes and 10 failures. When we're looking at numbers, we would do n times p naught has to be greater than or equal to 10, and likewise the number of failures would be n times 1 minus p naught. That also has to be at least 10, and then the population has to be at least 10 times the sample size. So let's take a look at an example. According to NPR, in October 2017, it was estimated that 68% of Americans supported stricter gun control laws. In February of 2018, a random sample of 1,005 Americans, 754 claimed support for stricter gun control laws. So do we have evidence that national support of stricter gun control laws has actually increased since that October 2017 claim? Or could this higher sample just be by chance? So in other words, if the proportion in 2017 was 68%, and we take another survey a year later and see that the proportion in that survey has increased, does that give us evidence that the actual population has also increased, or could this just have happened by chance? So what is the null and the alternative hypothesis? The null, remember, is that we assume nothing has changed, the status quo, whatever it was before, we assume it's the same. So we would say in this case that P is still equal to 68%. The assumption is nothing has changed, the population proportion is still at 68%. The alternative, since the question says, do we have evidence that support has increased, the alternative would be that P is greater than 0.68, more than 68%. So is this one-sided or two-sided? Well, remember, greater than or less than means you've got a one-sided hypothesis, and it's going to be a right-tailed test because of the greater than. So if we're looking at like a little sketch of the distribution, we expect 0.68 to be what we get for our population, but we got a little bit higher. Well, we'll see what we got in a minute. We got something a little bit higher than that, so we want to know, is it possible that the population proportion has gone up? So it would be that or more extreme. All right, so let's check our conditions. It said it was a random sample, so we can assume random and independence. We have to have a sample large enough for 10 successes and 10 failures. Now, the P naught that I'm talking about, that is the proportion from the null hypothesis, the 68%. So in this case, to calculate the number of successes, we expect to get 1,005 because N, remember, N was, 1,005. So let me jot that down. N is 1,005. So our sample size is 1,005. So 1,005 times 68%. I don't know what that number is, but it's certainly more than 10. And then the complement, 1,005 times 1 minus 0.68, that would be the expected number of failures. That would also certainly be larger than 10. And of course, the population of the United States is at least 10 times the sample size. So we're good to go there. They generally give you a level of significance, but if they don't, the default that we generally go with is 5%. So the alpha level, remember, is the 5%. That's the significance level. So if they don't give you one, you can just use 5% as your cutoff. Let me write that a little bit neater. So our alpha, let me write it down here. Alpha is 0.05. Okay, so if they don't give you that, you can just go with 5%. So then the next step is to go ahead and compute. So it says which date is representing the sample in this situation. So the sample is where we're going to obtain our p hat. That would be from the second date, February of 2018. So in February of 2018, we had, let's see, so p hat, here I'll put it down here, p hat was 754 out of the 1,005 that we surveyed, and that is a percentage of 0.75. 75% of our sample said yes, they favored more gun control laws. Now, let me go back here and fill in these blanks. The values in October 2017, those are considered parameters because we're assuming that 68% is the population proportion from 2017. In 2018, however, those are coming from my sample, so then remember those are called statistics. Statistics. Okay, so p hat, that's my statistic, that's 0.75. And then p naught is what we use to build the hypotheses. Let me go back for a second. This is your p naught right here, and that's based on the original population proportion. So in this case, p naught is 68%. And to calculate the test statistic Z, we're going to use the same format we've been using all semester. In fact, we used this back in chapter 17. The test statistic Z was p hat minus p naught divided by the standard error. So I need to calculate the standard error. So the formula for that, remember, is going to be the square root. I have to use p naught times 1 minus p naught divided by n, my sample size. So for me, that's going to be 0.68 times 1 minus 0.68 divided by n, which is 1,005. And I'm getting a standard error of about 0.015. So if we put this information together, we can calculate our test statistic that goes with this particular sample. So my test statistic, let me make a little bit of room here. I'm going to erase this, but I'm going to leave my standard error, that 0.015, so I can refer back to it. And my p naught, remember, was 0.68, and my p hat was 0.75. All right, so my z-score then, using that formula, is going to be equal to 0.75 minus 0.68 divided by my standard error of 0.015, and I'm getting a value, a z-score of 4.67. So if you think about visually what's happening here, let me go back to the picture I had on the previous page. This picture right here, 0.68 is what we expected, assuming nothing had changed, everything's the same. The population proportion of 0.68 is what we expected. Now, in my sample, I got a sample proportion rather of 0.75. So that corresponds to a z-score of 4.67. That's what we're saying. Remember, a z-score standardizes everything. So 0 would go in the middle for a z distribution, and then 4.67 would be my z statistic, or my test statistic, that goes with my sample proportion of 75%. Now, do you think that would be unusual? 4.67 standard errors above the expected value. That would be really, really, really unusual. Remember, anything outside of 2 standard errors is generally what we consider unusual. So we know it would be very unusual to be 4.67 standard errors above the mean. In practice, we usually use technology to compute the test statistic and find the p-value. So in class, I'll show you how to do this, or I'll make a video so you guys can see how to do this in StatCrunch, but these are the steps you're going to follow. It's actually the same steps you use to calculate a confidence interval. You're going to go stat, proportion stats, one sample with summary, and then you're going to type in the number of successes out of the number of observations for your sample, and then you're going to just make sure you check hypothesis test instead of confidence interval and click on compute. So based on what I would get in StatCrunch, here's what the screenshot would look like. They say P equals 0.68, that's my null hypothesis, and then P is greater than 0.75, that is my alternative hypothesis. So I had a count of 754, out of 1,005 observations. My sample proportion then is 0.75. My standard error was 0.0147. Now, I calculated this earlier by hand, and I got 0.015 when I rounded it, but in StatCrunch, a little more detail, 0.0147. And based on the way StatCrunch is rounding it, they're getting a Z statistic of 4.77. And then they tell you the p-value that goes with it, and they're going to say the p-value is less than 0.0001. The p-value, remember, is the probability. The p-value is the probability of getting a sample as extreme as 75% or more extreme. So in my picture, it would look like this, and this is the same picture I had on the previous page, but it's a good picture for you to think about. If we do it in terms of z-scores, 0 would go in the middle. So where would 4.77 go? That would be way out here in the tail. It'd be so far out that the test statistic, or the p-value rather, that goes with it, remember that's the probability right here of getting something as extreme or more as either 75% or a test statistic of 4.77. If the null hypothesis were true. So if the null hypothesis were true, in other words, if the population proportion were still at 68%, the chances of getting something as extreme as 75% would be very, very small. How small would it be? It'd be almost zero, almost impossible to get a sample with 75% in support if the 68% is still true. That's the key idea. So let's summarize this. Oh, here's a picture. I could have used their picture. That's all right. Let's summarize what this means, though. Okay? So what does the p-value mean in the context of the exercise? So that would be the probability of getting a sample with 75% is very small if the p equals 0.68 is still true, and still true as of the February 2018 survey. How small is that? That's very small, very unlikely, and very unusual. So does this give us evidence to reject the null hypothesis? Yes, most definitely. Remember, small p-values lead you to reject the null hypothesis. I kind of mentioned a significance level of 5%. So that's sort of what you want to compare it to if you're not sure. Always compare your p-value to that 5%. So if p is less than 5% or less than whatever your significance level is, that is when we reject the null hypothesis. So would you reject it? Yes, we would absolutely reject the null hypothesis. All right, so let's summarize what we're saying. Since the p-value is small, we reject, I'm going to just abbreviate because I'm short on space and say H naught. That's the null hypothesis. And have evidence to support the alternative hypothesis, which was that the population proportion has done what? The alternative was that the population proportion has increased above the 68%. So the alternative that the population proportion has increased. And so we have evidence to support that there actually has been a shift upwards of the proportion of people, according to at least February of 2018, that the proportion of people who support stricter gun control laws has increased. That's the logic here. So it's the probability, p-value is that probability of getting something as extreme or more extreme as your sample if the null hypothesis proportion is still true. So because that probability is so small, that means we don't think the null hypothesis is true. We have evidence in support of the alternative. So a little bit more about the p-value. The calculation of the p-value depends on the symbol used in the alternative hypothesis. So remember that if we have a not equal to, that means we have a two-tailed hypothesis. And so what that means, so like if your alternative is written in such a way that p does not equal whatever P naught was from the null hypothesis, then the way you're going to calculate this, or the way StatCrunch is going to calculate it, is you're going to have something on this end, a test statistic that's negative, so like a negative z-score, something on this end that's a positive z-score, and then the p-value that actually gets calculated in StatCrunch is the sum of these two shaded tail areas. So the p-value, remember, is the probability. Those are the shaded areas. So if you have a two-sided hypothesis test, this is what your p-value regions are going to look like. If you have a left-tailed test, so that was, well, we didn't do one today. That would be like if p is less than p naught, then you're going to look at your z-score. And your z-score, now, it can go wherever. It can go down here. It can be a negative z-score. It can go up here and be a positive z-score. Wherever your z-score is, though, the area that you're looking at for your p-value, you're going to shade to the left of it. Okay? So the region you're looking at is to the left of whatever the test statistic is, and that's your p-value. And then for a greater than hypothesis, so that would be the case where, let me see if I have more room on the next page. I don't. Let me go and see if I can squeeze this in down here. So the greater than would be where H sub A, P is greater than the null hypothesis. And actually, that's the case we looked at in the last example. Let me go back to my picture here. So my picture was like this, where my test statistic, we wanted to know the probability of getting a test statistic of 4.77 or higher. And so you shaded to the right. So when you have a right-tailed test, I'm going to put it here so we have enough room. Your test statistic, I mean, it could be, your z-score could be here. It could be down on this end too. It just depends on where your z-score is. But the point is you shade to the right of it. Or if your z-score were down here, you would shade all of this area in that case. But the p-value is whatever is computed by shading to the right of whatever your z-score is. And so that's what StatCrunch is computing when it runs the hypothesis test. All right, so let's look at another example here. It says, according to this website, this government website, 24% of college enrollees were first-generation college students in 2002. Has the current rate of first-generation college students changed since 2002? So changed since 2002. Suppose that 75 out of 300 randomly sampled college students are first generation. All right, so let's start with the null hypothesis. So the null hypothesis is the assumption that nothing has changed from the original population proportion. So in this case, that would be that P is still equal to 24%. The alternative then would be based on however the question is phrased. So it says, has the current rate of first-generation college students changed? So for that, we're going to say that P is not equal to 24%. So it could be higher, it could be lower. Is this a one-sided or a two-sided test? So because it's not equal to, we're back here, we're looking at the two-tailed test, not equal to. So it's going to be a two-sided or two-tailed, same thing, test. And then the results to the test are given in the display above. So you can notice, you got to look kind of close because it's a small image, but you notice that we have a distribution here where we've got two tails that are shaded in. And it's very hard to see in the picture, but up at the top here, they give you the information. Let me write what it says up the top. It says that the z-score is, let's see, the z-score is 0.4056, I believe. And the p-value that goes with it, so remember the p-value is the shaded area, the p-value that goes with it is 0.6851. All right, so the test results are given. Why are the two tails shaded? And the reason that they were both shaded was because it was a two-sided or two-tailed hypothesis. Now it says, what is the test statistic? And it says to compute this by hand. So I know the test statistic, it was the 0.4056, but just for practice, let's go ahead and compute this by hand. So remember to calculate the test statistic. My formula is going to be p hat minus p naught divided by the standard error. I'm going to go ahead and compute the standard error first. So my standard error in this case would be the square root of the 24% times 1 minus the 24%. Divided by n, and we surveyed 300 students, and so that gives me a value of 0.02466. And then, let's see, I also need p hat while I'm at it, so p hat would be my sample proportions. So what did they say for the sample that we surveyed 300 students. Out of the 375 were first generation. So my p hat would be 75 out of 300, which would give me a p hat value of about 25%. Okay, so I'm going to erase. I'm sorry, there's not a lot of room on here. I'm going to erase. So let me go ahead and write this out using the z-score formula, but let me make some space here. So my standard error, don't forget, is that 0.2024 number. And then my p hat, of course, is the 0.25. So if I put this together, I'm going to have 0.25 minus p naught. Remember, p naught goes with your null hypothesis, so that's the 0.24. Divided by the standard error of 0.02466, and I'm getting a test statistic of 0.406. Now, notice that the screenshot, they gave me the test statistic earlier. The screenshot they gave me, I wrote it up here. The test statistic was 0.4056. Based on how I've rounded, I've got 0.406. So the same test statistic they got. Now, then the question says, does the p-value that goes with this? Now, the p-value you would have to obtain from StatCrunch, and that's that number of 0.6851, that was my p-value. Does that give us strong evidence to reject the null hypothesis? No, it does not, because that is a very large p-value. Remember that 5% is kind of our cutoff if they don't give us a significance level. Well, we've got a p-value of 68%. That means this is not unusual. This is not surprising. This means that the null hypothesis, we cannot reject it. So we're going to say no, since the p-value of 0.6851 is large. We will fail or do not. So fail to reject H naught, the null hypothesis. So this means that we think the proportion of students who are first generation is probably still around 24%. We don't have evidence that it has changed from that 24% number that we started with.